Welcome back to part 2 of my knob project video. Like most projects, you learn by doing, making mistakes, then discovering better ways to get results. This knob project was no different. Part 1 covered a basic knob body less the shaft hole. After some hours of experimentation, failed efforts, printing limp biscuits, and other R&D efforts, I finally got a working knob design. A link is in the description to the FreeCAD model, which hopefully saves you some time. I've set it up for a 6mm rotary shaft encoder, which is a light-duty, low-torque application. A 3D print in PETG worked fine, which took about 20 minutes. The printed part met expectations. My rotary encoder has a 6mm shaft, which needed to be cut down to 5mm long. The knob has a grabber clip design that presses over the shaft. The wings allow spinning, and the dimple indexes a finger for push-to-select operations. There is very little torque or other forces in this application that might make the knob slip or fall off. A stronger design would include a brass insert and set screws. That's overkill for this application, so I went with a simpler approach. The model has been augmented to include a spreadsheet to enter design values. For those interested, I'll go through the model. If there's no interest in that, bail out here and just download the model and enjoy it. Per usual, please subscribe, like, and share your comments. Thanks for watching, and I hope the information is useful. Here's the model, and basically what was done is we enhanced it in a couple different areas. It's basically the same body that was shown in part 1, the cone, but I changed a bunch of things and I made some improvements. So let's just go through this and we'll see how this works. The first thing I added was a spreadsheet, and here's in green all your user design parameters, and the bottom diameter, top diameter in millimeters, height. That allows you to accept maybe a longer shaft if you need to. Here's the dimple, the depth, how far that goes in from the top, the diameter of that dimple where your finger can register, the length of the wings or the tabs, the thickness of those wings or tabs, and the number that you want on there. So you make this 1, 2, 3, or 4, whatever you want. This wing inset, I'll explain in a minute. It's a little tricky. And then, of course, there's the shaft diameter and then the shaft depth. So if you're going to have a dimple that goes down into the knob 2 inches for an 8-inch knob height, that leaves you with 2 millimeters into a knob height that's 8 millimeters. It's going to leave you with 6 millimeters of meat in that knob. So I just set the shaft depth at 5 to leave 1 millimeter of meat in the knob where the shaft bottoms out. So if you need more than that, you go ahead and just change these values around. So that's how that works with the spreadsheet. So let's go back and take a look at this dimple. Originally I had used a subtractive sphere, and I just kind of let that fall in here and create a sphere or a dimple in here. And it was a little tricky to figure out how deep you went and then how wide or what the diameter of that was going to be. So I actually came up with an alternative that I think is better, and that is creating a solid of revolution like this. So it's just a triangle. These are coming right off the spreadsheet. You just revolve this, then you get a funnel, and you could subtract that out from here, and that gives you a dimple. And then you can control the depth, and you can control the radius or the diameter of this dimple. It's real easy. So it's flat here or straight, not curved, but it's such a small feature of the part. I think the advantages of this far outweigh the straight profile. So that's what I did with that. The other thing was dealing with the wings. If you look at the top view here, these wings, let's go in here and bring this in. These wings have to inset into the body of the knob in order to prevent a gap along this edge right here. So before, in the original model, part 1 video model, I just winged it, no pun intended, and I said, minus 0.6, let's just dump it in minus 0.6 and just give it a little inset. So what I did, which I think is a little bit better, is there is in the spreadsheet functions, we'll go in here, this cath function, which is actually a triangle solver. So you can specify a hypotenuse, and then you can specify a side, and this will give you what the other side length is. So in this particular set of dimensions, that works out to be 7.68 millimeters, and where that is that's from the center all the way out right to this line here. So if you take the top diameter of the knob and you subtract from that distance, you'll get a little small inset, and that brings you right to this edge. And you do it on the top diameter because the bottom one is actually going to inset a little bit more. So this is the more severe of the two. So if you work from the top, you'll automatically pick up the inset. We can look at the bottom and you'll see what I'm talking about. Let's just bring that in. You'll notice here, you see it's inset just a little bit further. It's not right on the perimeter here of the or the circumference of the circle. No harm done. You get a little bit more inset in there. It makes it a little bit stronger. So that's how that works. So that's how we handled that, and it's an improvement. So regarding the shaft, which was the last thing I had to add, the knob is useless without the ability to put a shaft in it. So we'll go to the bottom view, and I had to create a cylindrical cavity, which is this right here, and I just simply did that with a subtractive cylinder, and that's what you're seeing right there. And these are values taken off the spreadsheet. I hard-coded some dimensions in here which are sort of constants, and that's the amount of distance that I allowed for these grabber tabs to expand. It's not really something that changes much if you change values for dimensions. So I just hard-coded that, and that's how we did that. And then I gave the depth to be equal to what the shaft depth would be. So that's taken right off the spreadsheet. So the tricky part was getting this grabber mechanism set up, and let's go back to an isometric view here. We'll leave that there, and we'll go in to the sketcher. And so here's that. This basically I figured out about 2 millimeters here, and that's also hard-coded, is a good amount of plastic to leave in this, so this grabber mechanism is stiff enough that it hugs the knob pretty well. The gap, I just made it 1 millimeter, again hard-coded. You can change that if you'd like. These are coming, this is coming right off the spreadsheet, and then I hard-coded some extra 4 millimeters above this all the time, so you get 2 millimeters of plastic. This was also hard-coded, and it's just enough meat to project into the body, so you've got a good secure connection between this grabber and the knob body. And the same thing here with the width. You can play around with these numbers if you like. You can change them if you need to, but that's the story with that. And here's the constraints. And the only glitch that I had was I over-constrained up in here, and that was kind of, it was a little frustrating to get that out. The solver kept telling me I had duplicate constraint, so I had to figure out what was going on with that, and I'm trying to remember here. Let's see. Yes, I remember now. This is kind of interesting. Let's go in here. You just need to make these parallel and then make them symmetric across this axis. And that's what I had a little bit of trouble with. But anyway, I got the sketch to be fully constrained. The solver likes it, so that's all worked out. And then all I did was I just padded it. And there you can see that right there. And that is basically a 0.5 millimeter hard-coded less the length of the shaft. And the purpose of that was to make sure that these wings that are expanding don't inadvertently connect to the knob body. There's got to be a little space. You'll see that if you look at the pictures of the actual knob, when you print it out, you look down in the shaft hole, you'll see it's unsupported plastic. It's a little ratty, but it doesn't really matter. The most important thing is these grabber arms here don't inadvertently get attached to the body, and they can move and expand when you press this down over the shaft. So that's it. I hope you have enjoyed the model here. Feel free to use it, play around with it, and thanks for watching.